Well, welcome everybody. Welcome to the October meeting of the Ottawa RASC. We've got some good stuff lined up for you today. A few folks that haven't chatted for a bit, and yeah, just a lot of stuff of general and very current interest there. So hope you enjoyed the program. Of course we're starting late, so that means we're already behind. But we'll try not to keep you too long. I think we've got a reasonable number of slides. Whoa, that's going to get really loud. Just back you off right there. We've got a reasonable number of slides tonight there, so I don't think we'll run over tonight. And Chuck's last up there, so Chuck, you're warned. All right. Tonight's program, we've got Gary starting things off with Ottawa skies. Al's got a really interesting 10-minute astronomy news update, a lot of current stuff going on there. And then Melanie Hall of the museum here is going to give us a talk on spiral galaxies and a little bit about herself in the world of astronomy research. We'll have our break then and draw for door prizes. We've got something special lined up for you tonight. A series of observations as well, and then Al Scott's going to come back and talk to us about ultraviolet telescopes. And time permitting, Chuck will talk to us about what was it, craters that you're interested in?
Hole in the ground somewhere.
Yeah, hole in the ground somewhere. So I saw the slide, very cool there. So I think we've got some good stuff lined up for you tonight. All right, no members in the news, so we're going to kick things right off with Gary Boyle. Come on up. There you go, sir.
Come on up, not down, up.
There you go.
Thank you very much. Good evening, everyone, and welcome to the October meeting. Let's move on to the next slide. Well, as the months go by, of course, the Milky Way is starting to set. We're starting to lose Sagittarius over here, along with Scorpius. Your last chance to see Mars pretty well, and Saturn is pretty well gone below the horizon. So it's still a good month to do some summertime, late summertime observing before the other flies are out, the snow. And next slide.
It snowed today at
Yes,
my place.
yes, even downtown. Downtown Ottawa, some flurries in the air. You didn't see me cry on the bus. Depressing. So one of the great constellations that's right overhead is Pegasus, the winged horse, the great square over here, like a baseball diamond of home, first, second, and third. 2 stars down and 2 rows up to the bleachers. Here we have the great Andromeda galaxy, and pretty well the same distance from Andromeda down to Merak. We go down to M33, and M33 is just a beautiful spiral galaxy, pretty well face on. There are a lot of NGC catalog numbers actually embedded in the arms, so it's really something to see in very large telescopes. And it's beautifully placed overhead, pretty well 45 degrees above the horizon. And next slide. And moving on past Andromeda, past Pegasus to Andromeda, we have Algol. First of all, we have Cassiopeia the Queen and the double cluster just over here. Pretty well counting the stars, 1, 2, 3, 4, and 5. You take 3 and 2 and just double the distance, you'll come to 2 beautiful open clusters of stars, 7,400 and 7,700 light years away. And if it's nice, see just in a binocular field. And coming further on down, we have Perseus the Hunter and the great star Algol, which is a beautiful variable star. And it's 92 light years away. Next slide. So the difference between Algol, between maximum brightness and minimum brightness, in just about 2.5 days. You can see how it flares up. Next slide. It's actually an eclipsing binary, which means it has a very, very close secondary companion, which at times, when it's off to one side, is at its brightest, and when it's in front or behind, it's at its faintest. And these are the minimas, or the minimum values or dates throughout the month. Next slide. The International Space Station is still passing overhead from time to time in the morning or in the evening. For the next pretty well the month, it's in the evening. I didn't put every date over here because there's just too many. We always look at the highest, pretty well almost overhead, extremely bright, minus 4.3 magnitude, almost as bright as Venus. So again, just get on my website, wondersofastronomy.com, and I do have a link to all the passings of the ISS overhead. And next slide. Well, 10 o'clock, 10 p.m., if you are a couple hours from now, Jupiter rises on the eastern horizon. And a couple of hours later, around midnight, we have Jupiter nice and high right next to Aldebaran of Taurus the Bull. Here we have Capella, the Pollux and Castor. So we really have 13 of the brightest stars, and of course, Mr. Winter himself, Orion. So it's really blazing in the sky before the snow flies again. So now it's a great time, pretty well, to do all your observing in one night. And next slide. And with Jupiter, there are many transits, too many to put on the screen over here. If you have the Observer's Handbook of the Royal Astronomical Society of Canada, there are many ephemeris of either a shadow transit, of the actual shadow of the moon, and the satellite transit, seeing the moon actually cross in front. And yes, this is Earth compared to Jupiter. You can fit 11 Earths across Jupiter's belt. In fact, Jupiter is giving out twice as much energy than what it's taking in. Hence, when it first was created, when it first grew, it almost became a second star, but it just did not have enough energy to undergo the thermonuclear reaction. Next slide. A couple of comets that are in the sky. Well, there are many comets in the sky, but a couple that will be in the news in a few months from now. First, we have comet Pan-STARRS, which is from Hawaii. It's mega telescope can pretty well map the sky in 4 nights, and it's picked up a very faint comet for now, but it'd be extremely bright in March of 2013. Should be a naked eye comet for sure. Next slide. So here we are past March. So it's pretty, and here's the great square of Pegasus again. So it pretty well favors northern observers here in Canada. And next slide. The new comet that's in the news is Comet 2012 S1. And this comet is, for now, deemed to be, or hopefully will be, the brightest comet in history. Some numbers being thrown out there, you probably see on the net, are -16 when it rounds the sun, which is, in fact, the full moon is -12. These predictions are early yet, because it's really this time next year, around November, December, to actually round the sun. Just like Comet Lovejoy round the sun just about the same diameter as the sun itself. So if it stays intact, as Comet Lovejoy did, we will get an extremely bright show. Here's the tail. Should be about 60 degrees long. And to see this thing during the day will just be phenomenal. So let's hope predictions are right and it just doesn't break up. Next slide. They think it could be associated with the Great Comet of 1860, or it could be just another 1680, sorry, or it could be just another bright comet from the Oort cloud that's never seen the sun, that's never had any of the gases and ices blown off it. And of course, here was Comet Lovejoy last year that the southern hemisphere really got a treat. So let's hope it's our time. Next slide. Here we have the lunar phases. Of course, we have the Hunter's Moon coming up on the 29th. And of course, that night, you must be very, very quiet. Thank you, thank you. And that's it for this month, folks. Thank you. And I'm taking money, as you saw before, taking money in checks. Our annual dinner is coming up 1 month from now on November 16th at Algonquin College. In fact, I just met one of the great culinary students in the audience who makes this fantastic food. And we do have Dr. Rennie Racine from the University of Montreal as our guest speaker. Quest for extremely large telescopes. So, and of course, mega door prizes just like last year. So I will be around during break. Unfortunately, I'll be leaving during break for the second half. I have to leave to go back home. But if not today, definitely next month will be the last time to buy it, next meeting. Okay, so again, checks, Royal Astronomical Society of Canada, Ottawa Centre, or Funny Money, not the Canadian Tire stuff. Thanks, folks.
-16 magnitude, you say, eh? Well, for the,
That's what they're saying.
yeah. Yeah, I was going to say, for the older folks in the crowd, remember, beware Cahutek. So, anyway, Al Scott, all yours.
All right. So before I start with the news segment tonight, I just have a couple of things I want to mention for the club. Elections are coming up again in the December meeting. We'll be taking nominations for some open club positions. We'll be looking for someone to fill Gary Boyle's role as vice president. We'll also be looking for representatives for national council. So if you've ever had any interest in how the club is working, please feel free to contact me.
This is supposed to be afterwards.
Oh, sorry. We're also looking for anyone who's interested in helping out with the executive workings of the club. Also, Stephen McIntyre, who's been acting as our club outreach coordinator, is stepping down next year, so we'll be looking for someone to help out with outreach. Stephen will still be around to organize the Science Fun Fest, which is coming up this year on this Sunday out at NRC Booth Street area. Free Science Fun Fest for the family is a great activity. So feel free to contact me afterwards if you're interested in getting involved. Thanks. Zoom back. Okay, so first item of business. Friday, September 21st, a meteor entered the atmosphere over Great Britain, delighting crowds. It was about as bright as the full moon and remained visible for 35 to 40 seconds through the atmosphere, fragmenting for at least the last half of that period. Meteorite trackers logged 564 eyewitness accounts from England, Scotland, Ireland, France, Belgium, the Netherlands, and Norway. A few hours later, another burst of 126 sightings was received from southeastern Canada and the United States, northeast. What at first seemed the unlikely arrival of two dramatic bolides in a single night might turn out to be something a little bit more interesting scientifically and historically. It's possible that the two events could have been from the same object, which was temporarily captured through atmospheric aerobraking, which is what NASA does when it puts things into orbit around Mars. It could have been a single large body that grazed the upper atmosphere over Great Britain, dipping to about 53 kilometers altitude in its first pass over Ireland before escaping back into space. But by losing the energy in the atmosphere, it wasn't able to escape, so it swung back around and then re-entered over North America. Interesting theory. There's still some controversy because the orbit isn't as well determined as people would like, and the velocity isn't well enough known to tell for sure. One meteorite expert suggested that it would have been an inclination of about 54 degrees. In its single looping orbit, it went out to about 6,330 kilometers altitude before coming back down somewhere south, somewhere in Ontario or Quebec. All sky videos show a fairly short duration re-entry event, and some people say it seemed to be too steep for that orbit, so it could also just be a freak coincidence. Anyways, quite a remarkable near coincidence if it wasn't a temporary satellite, but it seems like a kind of maybe a first. I don't think anyone's ever documented such a thing happening before, so it's kind of a neat idea.
You know what size the asteroid was, meteorite?
Not sure. They're thinking on the order of less than a meter, though. So this is a big tongue twister. There's a possibility that we'll experience in 2014 a new meteor shower, the Camelopardalicid shower. New calculations by people who track comets, tracking the 209P linear 2004 CB comet, suggest that it could cause a meteor shower on May 24th, 2014, around 7:40 Universal Time. Expected to be best visible in North America, which is good. There's a call for more observations of the comet itself to get astrometry, photometry, magnitude measurements to improve the accuracy of the prediction. Right now, they're predicting from the very limited photometric data available that a zenith hourly rate of 100 to 400 meteorites per hour is predicted. And this, I think I may be reiterating what Gary was just talking about, so I won't spend too much time. This is Comet 212 S1, or ISON. This was a announced on Monday, September 24th by Russians Vitaly Nevsky and Artyom Novichonok, who detected it in photographs taken 3 days earlier using a 15.7-inch reflector at the International Scientific Optical Network near Kislovodsk. It was detected at magnitude 18.8, and there's the picture of the detection image. And it's officially known as Comet C2012S1. As Gary mentioned, it's got, the orbit of this comet is strikingly close to the Great Comet of 1680. And it's a sun grazer, and that's why the predictions for its magnitude are so high. The 1680 comet was glimpsed in daylight, and later, as it moved away from the sun, it threw off a brilliantly long tail that stretched for 70 degrees. So this comet is going to whirl over the northern hemisphere after perihelion. It should become visible during December, both in the evening sky and after sunset, in the morning before sunrise. So that is it for the news. Thank you.
Thank you, Al. All right, Melanie Hall, good to see you. Come on up and tell us about spiral galaxies. There you go.
Yeah, there's a pointer,
You betcha the laser's right in the center there.
and you change the,
Or you can if you want.
Okay.
That's advanced and that's back.
okay, cool, thank you. So I have a problem because I tend to move around the stage a lot, so let me know if I'm over here and you can't hear me, because I'll yell a little louder, but I can't seem to stay in one spot. So today I'm going to talk to you about scaling relations in spiral galaxies. So I work here at the museum, but before I was here, I studied at Queen's University, and I did my master's research in scaling relations in spiral galaxies. So I'll explain the scaling relations part. Spiral galaxies, like the beautiful Sombrero galaxy that we have behind here. In fact, I never studied that galaxy. It's just really, it's kind of beautiful. So I'll be talking a lot about some of the stuff that I did with my advisor. Hang on a second. This one? Stéphane Courteau at Queen's University, and some of my collaborators who I worked with throughout the years. And this all culminated in a paper that was released in August that I'm quite excited about. So let's see. So here we start with the photo. This is in Hawaii. This is on Mauna Kea, and it's me and my collaborator. So this is my advisor, Stéphane Courteau. He was very instrumental in everything that I did. Obviously, being a master's student, I did not know very much coming into it. He was also my undergrad thesis advisor, but I had some great opportunities. As you see here, this is the Gemini telescope on Mauna Kea in Hawaii. We were lucky enough to be able to take this photo from the catwalk of the Canada-France-Hawaii telescope on a beautiful evening, and I'll tell you a little bit more about that. And all of my work was done at Queen's University before I came here. And I graduated in 2010, so it was fairly recently. So it all started, I did my undergrad at Queen's University, and I was the observatory assistant at the Queen's Observatory. So I don't know if any of you guys knew that Queen's had an observatory, but it does. And we run our open houses with the Kingston chapter of RASC, actually. So I've got to know them fairly well. This is a Taurus Technologies 16-inch reflecting telescope. It's extremely old, and in fact, it broke 3 months ago. And there's a very brand new telescope that they have installed there. I don't know what kind it is. I'm not there anymore, and they're having their inauguration tomorrow. So it's very exciting for them. A new scope. This one was old, and actually nobody could fix it for us when it broke. It was Taurus Technologies, and there's no longer anybody available to fix it. But I ran the telescope, our observatory tours, school groups, and stuff like that. And that's pretty much how I got involved in outreach and landed here at the museum. But I worked a lot with the instrumentation during my undergrad, and then as well during my master's. So this is sort of some photos that you saw before, again at the catwalk. I was lucky enough to go to Hawaii to work with collaborators, work on the mountain, work with the telescopes about 3 or 4 times during my master's, which is fairly significant. But we had a lot of collaborators at these telescopes. Apparently it's really beneficial to get people who work in Hawaii to work with you. And so again, this is on the catwalk here. This is back here. This is the Hawaii 2.2 meter telescope, which I did observe at, but not from the summit. That one you actually observe from another island at the University of Hawaii on Oahu. So we did observe through that one. It's an infrared telescope. The Gemini 8 meter telescope, we did some really great training there. So it's actually a queued observing system, which means that you don't actually go to the telescope and take your own data. There's an astronomer and a telescope operator there, and they will take your data for you. which is nice because if you have a really good really good images to take and your proposal went through and it was the best one, then you're definitely going to get your images. But unfortunately, there's no reason to really go here anymore. So I was very fortunate to be able to go here and learn about the telescopes and the instrumentation while we were collaborating with people, because these days you can do it from your living room. I mean, I've observed in my living room on these telescopes, and it's not as exciting as going there. So here, and this is just a silhouette, but these are the two Keck telescopes and the Subaru telescope as well. So again, learning the intricacies of some of the instrumentation is really sort of fundamental. This is at the Apache Point Observatory. This is John Holtzman, and he's sort of the guru of a lot of the telescopes there and some of the data processing that they do. This telescope actually provided all of my thesis data. This is the 2.5 meter telescope that actually takes the Sloan Digital Sky Survey. If any of you have heard that, it's a quarter sky catalog. I'll talk a little bit about it later. And it scans the whole thing. And actually, it's a square telescope. It's kind of weird. It's got these weird shutters that come out. And it actually sits in like a barn structure. And then it rolls out every night, and then they roll it back in. So there's no dome that opens. It essentially just rolls. It's kind of weird looking. And this is the back, and it's got all these actuators and stuff like that. So it was really good to go there and learn about the instrument that you're going to study. It's not just about the hardcore astrophysics. It's also about the instrumentation. This is... at computers. This is at Palomar, actually. That's, I think, the next one. So I've observed at the Palomar, the 200-inch Hale telescope, and that's in California, up on top of the mountain, and it's the biggest dome I've ever seen. It's got this huge telescope inside. I mean, the telescope isn't the largest in the world, but I think the structure might be. It's built, I think, by the same people that built like the U-boats or something like that. I heard a story. Some of you might know more about it than I do. But it was gigantic. And actually, when we were observing one night, there was something that went wrong with some of the flat fielding that we were doing. And I got to go up, the telescope operator had me go up in this, there's like a little elevator that goes up, and then you can sort of look into the telescope. It was the coolest thing I've ever done. And my poor thesis advisor had to stay in the control room to make sure things are going okay. He was so jealous. This is some of the instrumentation at the bottom of the telescopes. This is where the spectroscopy happens and stuff like that. And here I was essentially doing spectroscopic work. And at a lot of the other ones, it was photometric work, so just taking images of those galaxies. And my work really combined the two of them together. Not only was I lucky enough to work at some of these telescopes, but work with fantastic people that I learned everything from. Essentially, everybody in this image. This is where I learned all of my astronomy from. This image was taken at a Galaxy Masses conference at Queen's in 2009 that I organized with my professor. And there's all of his students here, which of course were my predecessors and knew the work and knew the data pipelines and the computing, and they taught me all of that. But also there's his advisor, Sandra Faber, right here. She's a bigwig in galaxy astronomy, and she's at University of Santa Cruz. And this in the middle, this woman is Vera Rubin, and she was actually sort of a pioneer in rotation curve, dark matter stuff, also very cool. So she's, I guess, my scientific great-grandmother. It was her 80th birthday, so we were celebrating her 80th birthday here, and it was really great. This is at the Institute for Astronomy in Hawaii. This is Brent Tully. He doesn't always dress like this, but he actually, he wrote a paper on the Tully-Fisher relation. He was the first person, and I'm going to be talking a little bit about that with my scaling relations. The Tully-Fisher relation is the original scaling relation, so it's very cool to be able to discuss some of the science with Brent. And this is my advisor here. We're observing in the background some infrared galaxies. That yellow screen, believe it or not, is the images that come out of the telescope. Really quite great, and that was in Hawaii too. So I really learned a lot from these people. This slide is a little out of place. It should have gone with the rest of the telescope slides, but I also observed at the 4-meter telescope here at Kitt Peak Observatory. And it's a beautiful place in Arizona. And in fact, the 4 meters where this picture is taken from, so you can't see it, but there's all these other telescopes on top. This is the Wind telescope over here. I think it's 3.5 meters. And the solar telescope here, this really big, long, shaft-looking thing. We went to see it, but I don't know what they do there. I'm not a solar observer. Okay. So that was the first half. Hopefully I did that fast enough so that I left some time for the last half in the science. It's really bright in here, isn't it?
I can cut those.
So many of you have probably seen this before, Edwin Hubble's tuning fork diagram. It essentially classifies galaxies into two main types, ellipticals, which are on this side, and spirals, which are on this side. It kind of gives you the impression that ellipticals evolve into spirals, but we know that that is not true now, though historically this is how it's been represented. So elliptical galaxies are the red and dead galaxies. So they're the reddest, they have very little gas, and they're very old stars. And the stars inside of them actually are in dispersion velocity. Oh, that's so much better. They actually have dispersion velocities, so they're all sort of buzzing around like bees. They have no ordered motion in the stars and the little bit of gas that's in there. And they're classified by morphological type. And then here you have all of the spirals at the bottom, the barred spiral galaxies, which for my purposes were essentially the same as the top, the regular spiral galaxies. Now, spiral and disk galaxies I use interchangeably, so it all means the same thing. So our S0, the lenticular, this is where my specialty starts, is on this tuning fork part. So the early type galaxies over here, we call them early, and late are over here. And again, that is just historical, because now we think that really these elliptical galaxies were formed from spiral galaxies merging, and they ate up all of their gas and dust, and they became these older elliptical galaxies with older stars. So I don't concentrate on any of these, just these ones up here. And of course, they can be at different viewing angles. You can see them face on, like this one. And so if you imagine a dinner plate, you're looking face on at the dinner plate. It's very circular, but if you turn it and you just get an edge-on view, it might look something more like this, more like a line in the sky. So there's a lot of more intricacies, whereas ellipticals, they kind of look the same no matter which way you look at them. So the galaxy rotation, this is one of my favorite galaxies, maybe one of your favorite galaxies too, though I never studied this one either. It's too big. This is M31. The Andromeda Galaxy, and it was originally studied by Vera Rubin and Ford in 1970 in their original paper, and they essentially are measuring the rotational velocity of these stars. So spiral galaxies are very ordered rotation in the disk. They have very specific rotations, and you can measure that rotation from the center all the way out to, well, as far as you would like. This is the stellar halo here. This is where the stars are. There's also a gas halo that extends probably a bit farther than that, probably about this far. And now we know that there's also a dark matter halo, but back then we didn't know. This is the rotation curve that they plotted. It's not exactly to scale. I sort of just plopped this on top of here, but you expect that the rotation, there's a little bit of rotation oddness in the center, because the center actually has stars going in velocity dispersion. It's not very ordered at the center, but as you go out, the disk starts to turn very orderly, and you expect a rise as the luminosity gets brighter, and then as you start to lose stars and start to lose gas, you would expect that it would obey the laws of the v squared equals 2 equals gm over r, and that's a Keplerian orbit, and that's what you would expect. So as you get less stars and less gas at the end, you would expect the velocity to go down. But in fact, in almost all galaxies that we measure now, and beginning with this galaxy, they saw that that was not the case. And this means that there is extra mass, extra matter in the outskirts of the galaxy, the dark matter now that we still don't really know how to describe, but we say it's there because this is what fits most of our models these days. So that is very important, because it tells us something, that the velocity does not have to do with the light in the galaxy. Yet, we can plot on this plot here, a Tully-Fisher scaling relation. We can plot the rotational velocity, so what we measured up top, here against the magnitude, or the intrinsic brightness of the galaxy. And we find that it's a straight line. This is the Tully-Fisher relation, and it says that the mass is somehow linked to the light, even though they don't follow the same characteristics when we look at the rotation curve. So it says something fundamental about galaxies. So it's been sort of a quest to find the best Tully-Fisher relation. We see that this has, I think his original paper had 17 galaxies, so not super statistically sound. But since then, there have been many studies that go about doing this. And this tells you, too, that if you measure the rotation of a galaxy, which is a distance independent, it doesn't matter how far away the galaxy is, you're always going to measure the rotation at the same way, whether it's next door or hundreds of light years away, billions of light years away. So if you can measure this, you can actually tell the distance, because this is an intrinsic brightness. which does depend on distance. So a distance-independent quantity and a distance-dependent quantity helps you map the size of the universe and based on where these galaxies are. So it's a very useful relation. Here is another rotation curve. This is just sort of to illustrate again. This is for our own galaxy, the Milky Way galaxy, that what we measure is actually a flat rotation curve. It doesn't go down like we would expect a Keplerian orbit to go down here, lower velocities where we don't see any stars, but clearly there is mass even though we don't see it. So I used the Sloan Digital Sky Survey, which I will call the SDSS from now on because it's kind of a long name. And it is that telescope that I was showing you that goes into a barn. And this is the front of it. It's kind of weird looking, but it's an automated telescope. It's actually a sky survey. So it will scan the sky each and every night. It's on a drift scan mode. It takes 53-second exposures in many bands. And it maps a quarter of the sky. And every few years or so, they get more data. And this group here, I'm not going to pronounce that name, they release another data release. And then you can actually download it from the internet. Anybody can download it from the internet. And that's what I did. So I went on the internet, I did a data mining sort of experiment, an exercise, and got as many objects as I could that were spiral galaxies that I was looking at. And I didn't get this many, but because these include stars and everything like that. But I did get a whole bunch. These are 9 of them that I got. These are all disk galaxies. So I had a list of galaxies beforehand that I knew were disk galaxies, and I know what I'm looking at. So the Sloan Digital Sky Survey comes in 5 bands. UGRIS is the name of them, and that was actually new bands that were sort of made up for the SDSS. Some people now use them, but essentially these are the colors of them. So this would be B. V is about the same as G. R and I are sort of the same thing, but they use different letters. They're slightly different bands. And this is a quantum efficiency plot, so you can tell that the U band and the Z band, not super useful. So we just threw them out of our sample, and we just used the G, R, and I bands for all of these galaxies. So in 3 bands, we could have this color data. And again, you ask the computer for those 3 bands, and it downloads it all for you, which is great. Now I need a way to measure the luminosity, so the brightness of these galaxies, because we're looking for rotation and the luminosity together to make a Tully-Fisher relation. So we need to make a surface brightness profile. I want to measure how bright this galaxy is from the center out to as far as I can in the radius. And what we do is we use these images and we place isophotal ellipses on top of the galaxy. Essentially, an isophote is an ellipse of equal light, so isophote, and there's a package that will do this for you, and you let the position angle and the ellipticity of these ellipses change, so it can twist and bend, but essentially it's going to follow the median light curve of each of these. So each along this ellipse, it's all the exact same surface brightness. And the next ellipse, the same thing. So as a function of radius, you can sort of calculate the light throughout all of these. Let's see what I have next. So this is what you get. So from these ellipses that I've done, you get, this is a surface brightness profile. This is the surface brightness on the left-hand side, so it's in magnitudes per arc second squared. It's a logarithmic value because it's a magnitude. And then you have radius. This is just in arc seconds, so it's not the absolute. Neither of these are absolute values right now. And it's galaxy UGC 5651. No particular reason. I think it was just a really nice image. So we can see at the center, this is the brightest part of the galaxy, so it's 0 radius, it's the inside, the bulge. So this is generally the bulge feature. And then you have this sort of straighter feature here, which is the disk of the galaxy, which is an exponential disk is what we assume for all spiral galaxies. This is an exponential, even though it's a line, it's in log space. So they're both logarithmic values, so this is exponential. And that exponential disk is very important in characterizing the different galaxies. So what we can do is we can fit a line, just a regular linear fit, to the outside of the galaxy. So we ignore the bulge because this has different dynamics involved. So we just look at the exponential disk, and we call the slope of this the radius. It's called the disk scale length, and we call it RD. So if you see this in some of my other plots, that's the disk scale length, and it's a global parameter. So really it takes into account the whole galaxy, right, from the center all the way out to the edge. You see at the very largest radii here, it sort of gets a little fuzzy. Our error bars are huge. It's because the galaxy is blending into the sky, and we can no longer calculate those faint light levels. So usually these don't have very much weight on what we do. You can also measure light quantities. So if you use this extrapolation to infinity, which is okay because the outside of the disk is very small, so it adds a little bit of light, not too much. We assume that the disk is exponential all the way out to infinity. You can calculate all the light inside, so just integrate under that whole curve, and you'll get the total extrapolated luminosity. That's why it's called luminosity ext. That's the extrapolated luminosity. But it turns out there's lots and lots of different parameters you can get from this. So you can get radii in 3 or 4 different ways, light in 3 or 4 different ways. One of the other ones that you'll see, we take the isophotal radius. So this is the radius at the surface brightness here of 23.5. So you just cut a line at 23.5 and you see where that radius hits, and it turns out here it's about 35. So that would be the R23.5 for this galaxy. Again, you can measure the total light underneath that curve. This is a very local quantity, so it really only tells you something about the specific place in this galaxy. The other one was a little bit more global, and you took the whole disk into account. So you can do this for the 3 different bands that we have, and I did do this for the 3 different bands. Here again, this is just the 23.5 isophotal radius here. Okay, so that was, so now we've got all of our photometry. So I did this lots and lots and lots and lots of times. There's an automated pipeline though, so really I just clicked go and waited for a while. But now we need our velocity measurements, and these come from radio observations. So we measure the 21 centimeter line in hydrogen. And this is done by collaborators at Cornell, the group of Giovanelli and Haynes. So they've written papers and they have all of their data available publicly so that we can then use their data and collaborate with ours and create a really nice sample of velocities and the photometry that I've done. So this is Arecibo, so some of their data was Arecibo, some of it is from the Green Bank telescope, all over. That's about 20 years worth of collected data from them. So it's a real gold mine, and it's great that we're able to share this stuff. What we get from their observations, this is really interesting, is that these radio galaxies, or the galaxies that they look at, the radio beam, the size of the field of their beam is much larger than the galaxy that they're looking at. So if their beam is this big, their galaxy is maybe this big. And it's actually just a great big light pot. So it's not resolved at all. So they just get all of the velocities that are in this one big beam. So essentially what you get from it is something that looks like this. You can't tell at what radius these velocities are taken from, but it turns out it doesn't matter, because this is the flux of the hydrogen in the galaxy, the rotating hydrogen, as a function of wavelengths. So this is as a function of wavelengths. So it's a double-horned profile here, and this is because the 2 edges of the galaxy are rotating. So one of them is rotating towards us, one of them is rotating away from us, and that gives us the Doppler shift in red and blue, and that shifts the line to either side. And then you can take this, the width here, and you know what the velocity of the galaxy is. So it's a really easy way, because you just stick a beam on the galaxy, integrate all the light, and then find the width. And they did this for about 9,000 galaxies over their whole catalog. So that was really nice, and I didn't have to do any of these, though it would have been nice to go to Arecibo. They did it all for me. And when you cross-correlate my sample of galaxies with their sample of galaxies, we end up with about 3,000 galaxies that we can do this game with. So now we've got, this is the scaling relation. This is the VRL relation, and it's velocity, luminosity, and radius. So it's presented in this sort of way for most of the rest of it. So this is the rotational velocity here. It's a log rotational velocity, so these are all logarithmic plots here in kilometers per second. And then on the bottom, we have the total luminosity. And this is now distance corrected. So here, the velocity, luminosity, this is the Tully-Fisher relation at the top on the left, but for 3,000 galaxies. And this isn't the largest sample that's ever been done, but it's a very interesting sample for other reasons, in that we can constrain some of the quantities really, really well. And so here we have a slope, we have the Pearson-R coefficient. These are just measures of how good this relation is. And we managed to get one of the tightest scaling relations, and it's very important for, like I said, measuring distances, but also if you want to create a model, a galaxy model, a formation model, it has to be able to reproduce these observations almost perfectly. So the better constrained your observations are, the better we can compare with galaxy formation models. And that's a really big part of the work that we do with our collaborators. At the bottom here, we have, this is the radius now. This is the R23.5 radius here. And this is, again, the luminosity. So there's also scaling relations in the radius and the luminosity. As you might imagine, it's quite tight here because they're both physical quantities, and they're related to each other through other variables. So it's quite tight, it's quite nice. And then we have, again, the rotational velocity here, which also correlates with radius. So we have three different scaling relations, the VRL, so the velocity, luminosity, and radius, and they all tell us something a little bit different about the galaxies and how they were formed. Now you can change the radius that we use, so I just changed the size. So this one is the isophotal R23.5. This was one of the ways to measure it that was very local, the radius. But then you can go and take the disk scale length, which is more global, tells you more about the evolution of the galaxy. And you find that actually the relation gets, in this corner here, they both get a little bit messy. And this is because of the fact that, that slope that we placed on that profile, it was that line, it could change a lot depending on your observations. And this is, again, something that we try to constrain and something that other groups try to constrain, and it's really hard, but both of these two plots are useful for different methods for different astronomers. We can also play this game where you can plot it as a function of morphology. So these are just spiral galaxies again, so the reddest S0 galaxies, and then the bluest SC/SD galaxies here. And you can see different trends as well. And then finally, what we do with all of this data is we try to create a stellar mass Tully-Fisher or a baryonic Tully-Fisher. And that means that instead of taking luminosity, which is just the stars, we want to take the stellar, so we want to convert it into a mass. And maybe this will tell us something more intrinsic about their relationship. Maybe it gets even tighter. And then the baryonic Tully-Fisher will actually incorporate the gas mass. So maybe this has something more to do with it. So you can do all of these things. You can get the stellar mass by multiplying the luminosity by a mass-to-light ratio. So this is the mass-to-light ratio. M over L times L will give you M. And these are just done by, these are stellar population models that you can find in the literature. You add the gas mass. We have the mass of the hydrogen gas from our collaborators at Cornell. And you can see here, this is the stellar mass, and this is the rotational velocity. So again, it has a really nice correlation here. Not much better than what we had before with the Tully-Fisher relation without the stellar mass. Here, the colors are kind of interesting. The reddest galaxies here, this G minus I is the color of the galaxy, and it's the reddest. These are the reddest galaxies, and they go over to the bluest galaxies here. Bluest galaxies are the younger galaxies, they have more gas, and so really you expect the gas fraction, which is here, this is the gas fraction of the bluest galaxies to be highest, the reddest galaxies to be lowest. So good, that works, because this is what we see in the plot, which is a relief. When we add those together, we can get M baryonic, so that includes all of the stellar mass and all of the gas mass. And we can make the baryonic Tully-Fisher, which in the literature has been sort of idealized as maybe the answer to all of our problems with the scatter of the Tully-Fisher and all of this stuff, and maybe the dark matter plays into it really well, and it turns out that we have a null result. It's great when you spend like 5 years of your life doing something and then you're like, oh no, never mind, it's fine. There's nothing going on here. So, but it's a good way to sort of advance the field and sort of say we have the largest sample of galaxies doing this type of thing with the gas mass, which sounds kind of small, but in our galaxy mass world, it's pretty big. So it's kind of exciting to see this result here. So I think that is the and that concludes with writing a paper with a very long name. So it's called Investigation of the Sloan Digital Sky Survey Imaging Data and Multiband Scaling Relations of Spiral Galaxies. So hopefully that is more familiar. So Sloan Digital Sky Survey, that is the survey that I used with that telescope and all of the imaging. So the imaging data and multiband, so the G, R, and I bands, the scaling relations, the VRL relation that I showed you, and the Tully-Fisher relation of spiral galaxies. And this was published in August. So that was the culmination of all of my hard efforts. And I do have another paper coming out soon, but it kind of depends on how busy they keep me at the museum and how much time I have to do it, but again, on galaxy masses. And I'll conclude, I have a little, so because now I do work at the museum and I don't do astronomy research as much as I used to, I'll have to point out that it is National Science and Technology Week this week at the museum across Canada, and it's very exciting. So hopefully you guys can come out to check out the website to see what's going on. It's like an across Canada thing. It has nothing to do with galaxy scaling relations, but I thought some of you might like to see it. It's a very exciting week for us. Thank you.
Just a quick question for you. You compile your velocity data with the radio telescopes, right? So that necessitates that you can't look at face-on spirals, right? Like they have to be tilted so that you can get the recession and the approach velocities, right? What's the limit on that? Like what kind of tilt are you looking at in terms of selecting those galaxies?
So it's actually twofold, because as you said, with radio galaxies, you can't get the face-on galaxies because the velocity would then be moving this way and you don't get any redshift.
Right.
But also when you're doing imaging, if you look at a galaxy edge-on, there's dust in the way from the dust lanes, and so you can't take much information about the radii and the luminosity unless you have really good corrections, which don't exist. So we actually cut our inclinations, so we use between 40 degrees and 75 degrees. And that actually is the difference between some of these plots where if some of you were close enough, you saw, okay, for example, in this one, you saw there's some smaller gray dots around, and then there's some darker black dots. And the black dots have actually been inclination cut, and the gray ones have not. So the gray ones represent all of the galaxies, which have some pretty wonky inclinations. And when we pare it down to just the inclinations that we trust, then we get the black relation in the middle.
Thank you.
Yeah.
I have a question. You've studied the various types of spirals. Now, for instance, you've got the SA, like M31, which is tight, large bulge in the center, and the arms close in.
Mm-hmm.
Then you've got the SC type, like M33, with a small bulge in the center, widely spread arms. Have you established how the various speeds of rotation vary between the type of galaxy?
Between the types of galaxies, that's a good question. We can actually, I've got this. So this is the rotational velocity as zeros, SAs, like you said, and then the SDs. And really, so the larger galaxies here are larger and they tend to rotate faster. So they have more mass. So they rotate a little bit faster.
There's would rotate faster than the SC.
Because they're larger.
Right, they are usually, yes.
Mm-hmm. Yeah, so the larger galaxies rotate faster than the smaller ones.
But you didn't go into the irregulars, did you?
No, I had a few in my sample, and then they don't work very well. And we had maybe 10 of them, and they didn't really work with our sample, and they weren't giving us the same dynamic information, right? Because it's not necessarily ordered rotation, so we made a decision to take those ones out. They really shouldn't have been in the sample in the first place based on the observations that were taken. So, but we did look at them, and they were sort of everywhere, and they were sort of down here. Yeah, they're local galaxies.
Study the ancient, the old ones that are billions of light years away, the original galaxies, the small ones. You didn't study those.
No, these galaxies are all within a redshift of about 0.1.
Oh, okay.
So a few billion light years, I think. Something like that, yeah. They're not too old. They don't have a lot of
These are mature
cosmic
galaxies.
redshift.
Yeah, mature
They're
galaxies,
close. Yeah, but not too close, because if they're too big, then our field in that telescope, they would just overtake the whole thing, which is another consideration that we took. If you can't see the whole galaxy, we're not going to take that image, because we're stuck with the field of view. Yeah.
Just a sort of a speculation question for you. Given the velocity curves that you've determined with this technique for the stars that have the rim vis-a-vis the ones closer to the center, that hints strongly at the presence of dark matter, right? So, what would be your best guess in terms of the ratio of visible matter in the galaxy to dark matter? Are they sort of equal amounts, would you think, to account for that rotational curve, or would the dark matter actually outnumber or outweigh the visible matter?
For sure outweighs the visible matter.
by a
So
large margin?
I think that the estimate, if I can remember, I used to do this talk a lot more often. The dark matter halo actually extends about 100 times, 10 to 20 times the size of the disk. So it's huge. So in that image of M31 that I showed at the start, the dark matter halo is way bigger.
So was that big?
So right now they're trying to sort of constrain the shape of that dark matter halo, and they're not really sure, and the shape would kind of help them decide how it was formed. And again, that's not really known. They know it's a triaxial shape, some type of sphere, but probably not a perfect sphere.
Right.
Yeah, so it's quite big.
Cool.
Yeah, and we have no idea what it is.
No? Super.
Thank you.
Thank you. Fascinating stuff. Thank you. All right, we're going to take a break. Our timing is actually very good. Just again, a reminder that Gary will have tickets for the dinner, so go see the man Gary there, and please do come up and get a ticket for the prize draw. All right, and we'll resume here in about 10 minutes. All right. Thank you.
And there was just a tube. And the little finder scope, there was no tripod. Some of the lock knobs were broken. It was lying derelict in the Salvation Army. For $3.99, there was no way I was going to leave it there. So I talked to Glenn LeDrew. Some people know Glenn. And I said, wow, this is what I got. This is what I've got. And he goes, starts looking at all this. And I'm saying, but of course what I'm missing on this was a star diagonal, which is this piece, which bends the light out coming from the telescope, bounce it up to your eye. Without this, it's more like a pirate telescope. You can look straight through, except that there's not enough distance to reach focus. I'd have to back this way out and even down another little bit. And with the mirror in here, that allows it to do that. So he said, I've got a 0.965 inch diameter star diagonal. Aha. Do you know the story of Stone Soup? The beggar goes to the castle, and he asks at the kitchen gate, could he please have he's very, very hungry, but he's not asking for food, could he please have a pot? Just a pot? Yes, indeed, and maybe a splash of water in it, and he builds a fire outside the gate. Starts boiling the water, and they say, well, what are you making? He says, stone soup. Well, what's in stone soup? He says, well, you don't, what I'm doing now is I'm going to go and I'm going to find some really nice smooth stones here. These look like good ones, and put them in the pot of boiling water. And he sat there by his pot. And now he's starting to attract a bit of a crowd. How can you have stone soup? That can't be very... He says, well, no, you're right. If I had some carrots, I would have put some carrots in. But, oh, well, we had carrots. You know, the carrots. And I say, and just carrots and rocks? He says, well, I mean, it's to your taste, too. I mean, I don't know if you like onions, or if you like potatoes, or if you like maybe a bit of beef, or whatever. We have all of those things. And then they go into the pot. At the end, the soup is ready, they taste it, and they walk away thinking, imagine. And all he did was he made that with 5 smooth stones. Here's the astronomical equivalent of stone soup. The tube, now somebody's throwing in a star diagonal. That means this will reach focus. It's a bit rickety, but I can tell you right now that even Galileo himself would have killed to have a telescope like this. We cleaned the objective lens, put it in the right way around, and cleaned it. But we still have a problem here. We've got this telescope. Okay, I guess you could hold it on your friend's shoulder and aim at the moon or whatever you're going to look at. So we talked to the good people at Focus Scientific, which is the main telescope store in town, and Tristan Young at Focus Scientific was very accommodating. And we said, Tristan, this is what we've got. Actually, the yoke that we had was broken, and this knob was broken, and there was no tripod. He said, come on with me. We went down into the basement of Focus Scientific, which is, it's kind of like a Middle-earth journey, if you've ever done that. It's interesting. So down we go, and buried in the back, there's this old tripod. This guy here had a new yoke from something else. There it is. And we were able to mount the telescope on there. The little arms that came across here to support the accessory tray were all bent. Somebody had bent them all down. So the telescope tripod was sitting like this. So if you just looked at it the wrong way, it was ready to keel over. So my friend Wayne, who does a lot of help with me, and he's a lot of help with me in my observatory with maintenance and that type of thing, he says, I can straighten those out and tap, 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 tap. He's very good working with metal. There they were. I would have snapped them off. That's what would have happened. There it is. So now we have a found telescope OTA, optical tube assembly, on a 60 millimeter diameter telescope. And we have a donated tripod underneath it. We have a donated star diagonal. We have cleaned optics on it. Now the thing with this is, there it is, it now has to find a home. This pot of soup needs a home. So what we're going to do tonight is, I'll ask, is there anybody in the audience who could really use a telescope like this? And if there is, I see your hand, Julia, I do see your hand in the back. And Peter Cerebolo, considering the optics you have to work with, I can see why you're interested in So what we'll do is we're gonna have a second draw. For people, can I ask, is there anybody here who's definitely interested in having this telescope? Don't be shy, because if you don't have a telescope, you would like to have it.
There's going to be one draw, so we're going to get you up for a second set of tickets for those that are interested.
Okay, you've got the tickets under control?
Yep.
Okay, can we have somebody then to go and
Yeah.
Bill there, if you can find the people and just do a ticket, okay? For the people, don't be shy if the three in your family, that's what you want, put your hand up.
Telescope needs a home.
I see you here. Brandolina, you said yes. Julia, you said yes, you're interested, okay?
And good luck to you, Peter.
Yeah, we don't. And just while we're handing those tickets, I'm going to show you how far this idea of sharing in astronomy can go.
Safety margin.
What somebody gave me tonight. Oh, upside down. Is a nice little drawing. Who did that drawing? Julia. Thank you very much, Julia. So she gave me this tonight, so that's the way we do it. I'm going to put it here while we're waiting for the draw, but I have to tell you the picture is coming home with me. I'll put that there. All right? Any questions about a telescope like this? 60 millimeter diameter?
What eyepiece is with it?
Oh. The eyepiece is, it's a Huygens design 25 millimeters, so this is a wide angle eyepiece. It's a wider angle, low power. And if you're just starting out with a telescope, you would normally want to work at the lowest possible magnification so you can see the largest amount of sky. That way you can find where you're steering around.
And the focal length of the scope, Brian?
The focal length on this, it's marked, all the information is marked right on here. Thank you, this is good. It's 700 millimeters.
Okay.
So when it comes to focus, you've got 700 millimeter. You can measure it with a tape measure, 700 millimeters.
So with that eyepiece, that'll give you just under 30 power.
Right.
Does it come with a solar filter?
No, but it comes with an auto guider.
Actually, while Bill's just finishing up here, we'll just be another minute. We'll get on with the draw. I was just actually thinking about solar filters because of this telescope. Some older telescopes come with a solar or a moon filter that screws into the eyepiece. If you have one of these, you find one at a garage sale, the moon filter is fine. Screw it in there, fine for looking at the moon. There's not enough light, you can stare at the moon like that all day long. It's basically just a bright parking lot. It just happens to be a big parking lot, that's why it's so reflective. But with the solar filters, putting the solar filter right at the eyepiece is a dangerous thing to do. You've got a cheap piece of glass, and what you've done is you pointed this at the sun's rays are coming in, you're now focusing the rays, you're building up heat inside this telescope, and right at the critical 2.5 centimeters from your eye, you put this cheap piece of glass. They've been known to crack under the thermal stress.
People have gone blind with these things. They don't sell them anymore.
If you find a little screw-in filter that goes in the eyepiece, get rid of it. Okay, the only safe way is to filter a telescope properly across the large end, so there's, it's cool. So are we ready to roll, Bill?
Actually, trying to get the world's cheapest laser. Current game.
Brian, I think you should draw this one.
Should I?
Absolutely.
Julia, can you want to come and draw a ticket for me, please? Will you come and help me? I'll ask Julia to come in.
She has a ticket.
Oh, she has a ticket? Oh, that's... Well, Bill, why don't you go see Julia? She can do the draw there. Is that okay? Okay. All right. See her there? Where? No. She's at the back post. Oh, is she coming up? Of course. Okay, come on. Oh, here's that would be good. I always like to have the artist alongside her work as well. So. Alrighty. Well, good luck everybody on this stone soup telescope. Hey, great purse. Look at this. All right.
Nice, bunny.
So we need one ticket out of the box for Bill, please. Can you?
You're a bad man, Bill.
Go ahead. Pull one out. There you go. Give it to Brian.
What have you done to your thumb? Oh, I have to talk to you later. All right. So the winner is the last two numbers, 65.
There we go. We have a winner. Enjoy your stone soup.
Oh, we don't look at numbers here. I absolutely refuse. If somebody says they got the winning ticket, I absolutely refuse to dispute that. You got the winning one? So there you go. And we'll take it over to the side. And have you used one of these before? All right, I'll show you how we'll be able to lower the tripod and all that. And I'll tell you some things about it, or maybe some other people will help you with it. What's your name?
Sarah.
Sarah? There you go. Okay.
Awesome.
All
Thank
right.
you.
Congratulations, Sarah. Okay, Tim, could I get you to cut the lights there? We're going to dive right into the observations. Here we go. And one more here. Oh, there, I think we're... Yeah, there's still two on the screen there, if you can cut those, Tim. I don't need a light on the podium.
Maybe just a little bit because the camera is too dark.
No, they're still there. Ah, perfect. Okay, great. All right, we have some good observation reports of some of our regular contributors there, some pretty cool imagery there. First up is Paul Commission, but Paul has asked me to talk to this one because I had some minor involvement in it. Just to give you a bit of history, Paul Commission has had a few of the kind folks at the RASC helping him out with doing some mechanical upgrades on his telescope there. Glenn LeDrew, I know, has been over there, and Gary Susek, and yeah, they've been helping Paul to alleviate some tracking errors and such, because Paul got a new toy. Paul bought a new camera. So for the new camera, he needs a telescope that will do longer exposures. Gary's found an auto guider for him there, and so I've been helping him sort of configure these things there. Because he's going to need longer exposures for his new camera. He bought himself a new Malin cam. Not just any old Malin cam. This is one of RASC's brand new Universe cameras. So this camera is one-shot color. It's 6.3 megapixels, so it's not a video chip. It's a CCD, a proper CCD camera for astronomy, 7.8 micron pixels, and APS-C class sensor. So we're just shaking out the bugs there, and Paul's auto guider, I believe, is on the way there. But to do some initial exposures, some initial tests with it, Glenn was helping him out a couple of weeks ago, and to eliminate the tracking errors on that, he limited himself to about 1 minute exposures. Now, Paul's telescope is a 14-inch C14 at f10, so not fast optically, but he's got a focal reducer in there, which brings it down to f6.3. So running at about 2,240 millimeters of focal length at f6.3. So good test object for a first test was M27, the Dumbbell Nebula. And that is a raw image. That's a 1 minute raw image from the telescope there. And It's very noisy because, strictly speaking, it's not a long enough exposure for this type of object. We need to go a little bit deeper, and that's why you need an autoguider, because without the autoguider, you tend to get sausage-shaped stars there. So once you get the autoguider in place there, typically you might, on an object like this, you might shoot 3-minute subs or 5-minute subs, that type of thing. We'll just have to experiment once everything is in place there. But the Dumbbell Nebula itself, we've seen many pictures of it. It's in Malpecula. It's about 1,150 light years from here, and it's a planetary nebula. So Paul collected 5 or 6 of these images with Glenn LeDrew, and when I came over, I saw them, and I said, you know, we can still probably pull some really good data out of this, even though it's 1-minute exposures. And once you get your autoguider in place and do longer exposures, we can go even deeper. But so what I did is I took 5 of the images, stacked them, and processed them, and we got that out of it. So this is effectively a 5-minute exposure, 5-minute exposure unguided. So I think your camera is working, and thumbs up to you, Rock. I think you've got a winner there. So good stuff. Good work, Paul. All right. Next up, Gordon Webster.
And assistant.
And assistant, that's right.
Okay, my first one here is Campbell's Hydrogen Star. It's a planetary nebula in Cygnus, and it's just a faint, very round nebulosity around the central star. There was I didn't have a really good note in my log, but I think there was a slight red-orange tone to it. That's at 187 times with the UHC filter. Next, please. This one I'm really pleased with. The sketch isn't quite as good as I'd hoped, but it's the Crescent Nebula, NGC 6888, again in Cygnus. My logbook's got about 40 entries in there of failed to find the Crescent Nebula. Kept looking. This is from my backyard in Orleans, which is very close to Place Orleans and the Park and Ride, and so there's lots and lots of light pollution. And this is actually a composite of 2 nights sketching. The center one is the laser?
Yes.
Okay, so this part through here, I picked up fine the first night, and then subsequent observations the second night, I managed to get the southern portion. And I was able to, and that's with an 03 filter at 88 times, and that's with the 12-inch. And I was able to confirm that a couple nights later at the Star Party, the RASC Star Party in Cumberland. Next, please. On Monday night, Thanksgiving, I had a security watch at the Rockcliffe Yacht Club, and just after dark, what did I see but this green thing in the sky? And I was playing with my new belated Father's Day present, a Canon DSLR, and got this and a bunch of other photos, but this one seemed the best with the Big Dipper in there. And I also did a sketch. And that's just drawn just with pencil on white paper and then reversed in the computer with a little bit of color added. Thanks.
Thanks, Gordon. Next up, Bob Olson.
Ever since Neil Armstrong died, I wanted to get a picture of his crater, and the crater is roughly there. I have a problem though. The crater is about 2.5 arc seconds across, and my camera, the seeing in my area is around 2 arc seconds. So this makes any visualization of that pretty tough. I usually use my camera at 1 arc second per pixel, which gives me a nice coverage of the sky, but I need to do better than that. So I took out the focal reducer and went to half arc second per pixel. And so I also realized I had to stop the seeing, so I had to shoot more exposures. So This is the area that my camera covered when I took the picture. And this is the picture. And what I did was to help get through the seeing, I took 200 images at 1/100th of a second, so that hopefully the faster exposure would stop the seeing. And unfortunately for me, I stack my images in a program called Maxim, and it can't stack this kind of image. So I had to use a lunar stacking program called, I think, Registack 6, which I'd never used before in my life. And it's the most friggin' unintuitive program on the face of the earth. With all kinds of sliders, which I had no idea what they did, so I spent a couple hours moving these sliders around and stacked 100 of my 200. I took the 100 best. And so this is the image I got, which is not too bad. There are the things that I was looking for. Apollo 11 is just where it landed. I actually can't see the lander. And now, this is strictly a crop, not another image. And when you crop down to this is what you see. And then labeled are there. And they show up pretty easily, I think, except for, of course, for the lander. I was so excited by this that I thought to myself that I could put an eyepiece in and actually look at it, and then I came to my senses and didn't. Thanks a lot.
Thanks, Bob. Okay, Rolf.
Okay, so have you all been looking at Jupiter? You got to get up like at 4 in the morning, but there it is. So anyway, so this is on September 16th, and right there you can see Europa. And what's interesting is on this particular night, you had the great red spot and also the small red spot, and they were perfectly lined up. And hadn't seen them lined up perfectly like that before. On the other side of the red spot is this area of turbulence. The red spot is probably a storm of some sort. Probably an asteroid or something lies underneath the red spot and keeps this storm going. But then there's all this turbulence on the other side of it. Does anybody know what this is?
Shadow.
I don't know what it is. It's what they call a barge. It's one of these things, only it's there. It's not. It's just a dark spot, but you'll see it in a later picture too. It's not the shadow of Europa. So Europa is pretty small, as you can see. This is, I guess, pretty much the other side of Jupiter. And September 24th, you also see a lot of white spots and different colored spots on it. And this was a few days later, and at that time Ganymede was fairly close to Jupiter. There's Ganymede. And I'm not sure if you can tell on that, but there's quite a few features actually visible on Ganymede there. So we'll just crop that and take a closer look, and there's Ganymede with all the features visible on it. Ganymede itself, I think, is around 2 arcseconds in diameter. Maybe a little less, I'm not sure. So, could that just be garbage or something on it? Anyway, so what I did was I downloaded the JPL simulation, which is on the right, and that's the image I took on the left. And you can see that most of the features line up pretty well. Is Simon here? He could probably name a lot of these features. I don't know. But obviously this dark, very dark feature here shows up here as if there's a little bit of a bite taken out of it. And I'm sure that's got a name, and Simon would know it off the top of his head. Now what's interesting here, this is, like I say, the simulation from the NASA JPL site. When I first simulated it, you enter in the date and time and where you're observing from. So I picked Earth as the place I was observing from, and entered the time and everything, and it was way over here. I thought, what's going on? So then I realized that NASA doesn't know everything. Apparently, they didn't take into account the light travel time. So I had to set the time actually 38 minutes earlier, which is the light travel time, in order to get Ganymede at the right relative distance from Jupiter. And yeah, somebody pointed out to me that they did actually note that in their frequently asked questions. They actually say in there, we haven't figured out yet how to account for light travel time. So there you go. But it's a very useful site, and it'll simulate all the bodies of the solar system. I blurred it a little bit and hoping to get some more similar view to what I was able to capture. So finally, this was just a few nights ago. This was with a 6-inch telescope and DSLR. I didn't bother trying with the C14 that night, but what you can see here is those same 3 objects: the great red spot, the small red spot, and that barge. And everything on Jupiter moves at a different speed. What you're seeing here is the atmosphere, essentially. So things move at different rates. So the small red spot is moved relative to the great red spot, and this barge is moved a little closer into the small red spot. So that's just, if you just have a 6-inch telescope and a DSLR, you can also take pictures of Jupiter. Okay, awesome.
Well, thanks, Rolf. That's certainly one of the finest images I've seen of Ganymede, the surface of Ganymede. That's quite an accomplishment, and you got to wait for those special nights of good seeing for that kind of detail. Excellent work. Last up, oh, that's me. Oh, that's right. IC 1396. This is an object that I've been quite fascinated with for the last little while. There's a lot of detail in this object, and I've shown you some images that I've taken of it previously, and but I wait for certain good nights to get the best results, because I was doing a lot of narrowband imaging on this as well. So just to put it in perspective where this is, this time of year, the summer triangle is tilted pretty much on its side there. I think I have the time set for about 11 o'clock or so. And the object is near Cephas, so just a projection there from Stellarium there, and we'll advance it one. So this is a very wide angle view of the same region there, showing the Milky Way and the summer triangle, stuff you can see certainly with your naked eye in Cepheus there. A little less obvious unless you're under very dark skies. Is the North American Nebula, and my object of interest, IC 1396. So this is the area here that I'm going to be zooming in on. The next shot just sort of concentrates on those 2 objects. And we have, again, the North American down here, and the Pelican here, and IC 1396 up here. So this is the object that's been sort of keeping my interest there, and you can see there's some dark dust lanes and all sorts of interesting stuff happening there. This region itself is a concentration of interstellar gas and dust, and it's being illuminated. It's sort of surrounding the star cluster of IC 1396, and being illuminated by a number of the brighter stars there. So again, the next shot will zoom in on this guy. And you can see the nebula itself there, and this is a broadband image, in other words, with full color across the visible spectrum there. And you can see this is the object that I've been really interested in. This is the Elephant Trunk Nebula. And I think I've shown you a few of those before there. One more zoom in for the next one there. I'm going to look at just a close area down around here. And that's the Elephant Trunk, again, in broadband. It's a very dynamic region. This is about 2,400 light years from Earth. There's a lot of action going on here because of the number of very bright stars in this area. They're causing the gas to be ionized, and certainly there's some compression going on here. A couple of the a couple of the stars in that cavity, they're believed to be responsible for actually hollowing out that cavity. So that's in broadband, and I thought I would really like to see what other kind of processes are in place here. So what I did in addition to the broadband imagery is I shot also 4 narrowband images of this region. So I was shooting this also in hydrogen alpha, hydrogen beta, sulfur 2, and oxygen 3. And then I took those narrowband images and combined it with the broadband data for my last image, which is that guy. And you can see how the advantage of the narrowband stuff is that it really brings out a lot of the differences, whereas if you're looking at this, I mean, there's a lot of red going on there, right? But here you can see that there's a definite variation in the processes. These edges of the elephant trunk formation itself are getting really charged up by the ultraviolet radiation coming off the brighter stars in the cluster. And interestingly enough, in the elephant trunk itself, just back in 2003, they using an infrared telescope, they discovered there's a number, about 8 or 9 stars, very, very young stars, basically that have turned on just in the last 100,000 years or so. So very, very young as far as stars go. So we know that interesting formation is also a star forming site. So I see 1396. So now I can turn my attention to other objects there. Now that I've pushed that one about as far as my equipment will let me go there. So an interesting object to study for sure. And under ideal conditions, under a dark sky with a sufficient telescope of sufficient aperture, you can actually see that structure. Although it is a bit of a challenge. So, thank you. Yeah, I was pretty happy with the way that turned out. It was, I think in total, there's about 5 or 6 hours of image acquisition here across the narrow bands, and the broadbands, there's probably about 3 times that much time in the processing side of it. So a big part of astrophotography, which actually leads me to my last slide and my shameless advertising. I should have showed this last month, but I forgot. I am actually giving a course in astrophotography down at the School of Photographic Arts in Ottawa. The first segment is tomorrow, and the second segment is next Saturday. So if there's anybody interested, I apologize for not talking about this last month, but if you are interested, come on down to the school or come and talk to me afterwards, and it starts at 9 o'clock tomorrow morning.
Question on this particular
Yes.
picture.
Mm-hmm.
Very, very interesting. You got a circular formation formed around. You notice this.
Mm-hmm.
Is that all part of the same possible explosion? Or is it part of the same nebula? Do you know,
It's part of the same nebula. It's not really an explosion. This isn't a supernova remnant. This is a concentration of interstellar gas and dust associated with the cluster of stars itself.
the cause of the circle would be what?
Just where there are denser regions there and their proximity to the stars that are ionizing it. Like really any part of this nebula could be likewise energized, but it depends on, you have to remember this is a 2-dimensional view of a 3-dimensional object, right? So wherever these dark or these denser areas of the cloud exist, if they're in sufficient proximity to the brighter stars that are pumping up the cloud, that are ionizing the gas there, they're going to be pumped up with respect to the background areas of gas and dust, which aren't nearly as energized. That's why you've got these very active regions along the edge of this formation there. It's a dense part of the nebula, and it's really being pumped by those central stars. Okay. So again, if you're at all interested in this, come talk to me after the presentation, and I can give you a few more details there. And that's all I've got for that. For me anyway. Yeah.
Nope, one more.
For me?
Yep.
What have you done? What have you done? Oh no, I was thinking about imagery. Okay. So other note here, we have our annual meeting coming up, and we always give out the Paul Commission Observer of the Year award. So I think we can. Oops. Glad you did that on me. So that Observer of the Year, that could be you. but I need observations and submission of log notes, pages, photocopies of any logs that you kept or notes that you've taken. I'll also be looking at all the imagery that's been submitted in the course of the last 12 months there, and then we will determine the winner of that award and announce that at the dinner. Okay, so please, if you can get those to me for the next meeting, that would be super. That would give me plenty of time to look through everything. So don't be shy. Send me your notes there, or you can contact me by email as well, okay? Super. And yeah, that's it for those announcements. Al Scott. Al Scott is up, and he's going to talk to us about the CASTOR UV telescope. And there you go, sir.
Thank you. Okay, so talking to you about a study that we did for the Space Agency, actually, for a next generation telescope, Canadian-led telescope concept for the ultraviolet. So I wore my purple shirt in recognition of that. So you can see there's a big team involved in this, and CASTOR is actually an acronym for the Cosmological Advanced Survey Telescope for Optical and Ultraviolet Research. And this is roughly the same paper that I gave at a conference on ultraviolet astronomy, Hubble and beyond, this summer in Kauai, which was mainly the U.S. Astronomers looking at what's going to happen after the Hubble is deorbited. What's the next big thing? And they were mostly concerned about these big 2.4 meter dishes that they're basically Hubble clones they got given by the National Reconnaissance Office. And this is kind of a more humble idea, just a 1 meter class Canadian-led telescope. And this goes into a little bit about the background, what the science that you can do with a scope of this size, and something that's relatively affordable for Canada to actually lead. Now, right now there's not a lot of money in the Space Department at Canada, but something like this on a small satellite can give very good scientific results in a very interesting area of science for a price that's relatively affordable to Canada. And the target of this is dark energy as a scientific goal. Dark energy was discovered in '98. There was a Nobel Prize awarded around 2011 for the discovery of dark energy. Dark energy is the label we give to the accelerating expansion of the universe. And this observation was made, this graph basically shows you what astronomers understand, why they understand that this dark energy exists. And this graph up here basically shows you brightness of standard supernovae. So using type 1a supernovae, which are expected to be the same brightness no matter where they go off, because they're created by the collapse of a white dwarf, which is gaining mass. And as soon as it gets beyond the Chandrasekhar limit, which is this mathematical limit of an electron degenerate star, they collapse, and they have the same amount of mass in it, and all the mass is turned into energy all at once. So astronomers expect them to be the same brightness. And by measuring the brightness on one axis and the red shift on the other axis, which is a proxy for distance, you would expect to get roughly a straight line. And if the universe is contracting, then that line would curve a little bit in one direction. That's what astronomers were expecting. They were expecting that the gravity of all the galaxies in the universe should be slowing down the expansion of the universe. So they expected to see that this curve would go in one direction, and what actually they discovered was it's going in the other direction. And that was a huge surprise, and that's why there was a Nobel Prize, and all of physics is turned on its head. And suddenly, we find that because this isn't exactly a straight line, here's the residual of all these supernovae that they plotted. You can see this is what they expected to see, and this is what they got. And this means that the universe is actually accelerating rather than decelerating. So it's actually moving faster. And what's causing this? Nobody knows what's causing this. This wasn't expected, so they called it dark energy. So now everyone feels happy. We understand it now. It's dark energy. And to actually cause this amount of expansion, roughly 72% of the energy, mass energy in the universe has to be dark energy. And the reason that is, it's actually not very dense. but the fact is that there's a lot of space out there that there's just nothing in there. So the density of dark energy is very low, but because there's so much space, it takes up actually 72% of everything there is. And then the dark matter that Mel was talking to you about that makes those galaxies turn fast, that's another 23% of everything. The stuff that we actually know about is this little slice here. So we don't really know much about what's out there. We know about, 4% of everything is ordinary matter, and all the rest is dark energy or dark matter. So the idea is that we need to do a little bit more mapping of the distant universe to really understand what's going on. And that's what this telescope is going to help us with. So there are several different international plans to tackle this dark energy problem and map the geometry of the early universe. The European Space Agency is putting together Euclid, which is basically a wide field explorer to look at all the galaxies and map them, map their distances, their redshifts, so by measure their color and their brightness, and try and map the geometry of the universe and the shape of these things and how they're distorted by dark energy and dark matter. And the Large Synoptic Survey Telescope in the US is a ground-based facility which is going to fill in some of the bands. The Euclid is actually just looking in the infrared. It's going to be an infrared telescope. So you need to get the blue bands as well so that you can fill in some of the data. So the Large Synoptic Survey Telescope is supposed to do that, but it's not going to see first light until 2019. So, and WFIRST is the US's version of Euclid, and it's not funded yet, so we don't know what's going to happen there. They were thinking of using some of these 2.4 meter dishes for that. So what is CASTOR? CASTOR is a complementary space telescope to Euclid, nearly diffraction limited 1 meter polar orbiting space telescope focused on wide field ultraviolet imaging in the blue and optical as well. And this is almost like a successor to the Hubble. And this is one of the highest priorities in Canadian space astronomy. You can see this is a picture of Andromeda in the ultraviolet from the GALEX mission, and we're overlaying the fields of view of the Hubble and the CASTOR imager. So at 1 meter you can have a much larger field of view, but by diffraction limiting this thing in the ultraviolet, we're almost getting the same resolution as Hubble over about a 200 times more field. And that's pretty cool. This shows you the survey area that Euclid is planning to do. This is galactic coordinates. So the galaxy runs along here, the Milky Way galaxy. This curvy thing is kind of the plane of the solar system overlaid. So if you're in a polar orbiting space telescope and looking away from the sun as the Earth progresses, you would be looking along this line here. So you'd be going up to the galactic poles, then through the galactic equator. As the year progresses, you go through the galactic equator, then back up the other pole. And what we want to do with this telescope is to overlap the fields of Euclid so we can fill in the bands faster and get this data before the Large Synoptic Survey Telescope at much higher resolution than you can get from the ground. So the surveys we want to do with CASTOR, we're proposing to do are kind of these overlapping surveys down to a magnitude of 27 in the U band, 28 in the G band, and as well do a really deep survey overlapping the Euclid deep surveys that are planned. Euclid is pretty well going to go ahead. The Europeans are in the phase B and they're moving ahead with this, so we're pretty sure it's going to go ahead, and we'd like to be complementary to it. So in terms of uniqueness and innovation, you can see the wave bands here. This is a plot of the wave bands, and you can see the effect of the atmosphere. These are atmospheric transmission curves at different altitudes, and you can see that a lot of this blue stuff from the ground gets wiped out as water vapor passes over you. CASTOR basically fills in these particular bands and is very complementary to Euclid. Now what does this mean in terms of discovery potential? What science can we get out of this? Well, you can see I think Melanie was mentioning the Sloan Digital Sky Survey. This is kind of the resolution of Sloan. This is the resolution that the Large Synoptic Survey Telescope is expected to get. This is the resolution that we expect to get from CASTOR by being above the atmosphere. Very sharp. And what this is kind of a plot of intensity or flux in an astronomical unit called millijanskis, which is very confusing, and you always have to just look up the conversion factor to real units. And then on this one, this is field of view, omega, divided by resolution. So it's a graph of information, spatial information, versus intensity. And these dots are various different survey missions that astronomers would recognize, and I'm sure Mel would recognize some of these. This is the planned Euclid Deep Survey. And so what we see is the Castor Deep Survey and the Castor Wide Survey are plotted on this, and information or discovery potential is going in this direction. So you can see the discovery potential that you can still get with a 1 meter space telescope really is up there with all of these big multi-billion-dollar missions that they're proposing. I'm not going to go through this. It's a dense eye chart here. Just shows some of the science that the scientific team led by Pat Cote at Herzberg Institute have come up with, and some of the questions that we think we can address in this area. We don't know what science we're actually going to be able to tackle because, you know, until you build it and look, you know, we think that there are certain questions that this will be able to give us answers to, but it will also give us new questions. And it's a huge, wide-ranging, transformational potential. And I'm not going to bore you with all of these things. You can see, you know, faint galaxies, nearby galaxies. We'll be able to measure the metallicity in stars in nearby galaxies. We're going to be able to do resolved star searches in nearby galaxies. We're going to know all about populations of stars in our own galaxy and measure their evolutionary history. So it's a really interesting mission. We'll also be able to do all sorts of interesting things with cosmic structures and dark matter. So what this is a plot of, this is what we need to do dark energy studies. We need to plot the photometric brightness versus the photometric redshift. So Z is astronomers use that for redshift. It tells you how far something is. And what we can do is we can use the bands of Castor to estimate the redshift, knowing that hydrogen alpha is the main emission line that we're going to be seeing. And we know that, so what the color of the galaxy is, it tells us a proxy for the distance. And this is the actual redshift along the bottom. Euclid, because it's limited in only the infrared, isn't going to do a very good job of getting a straight line here. That's what this plot basically shows. If we add in the Castor data, we're getting a much better idea of the distance of these galaxies, or the redshift. And then if we add in the Large Synoptic Survey, we're going to get a really good idea. And these are the sort of limits that we need to do some really good science with this and really establish the geometry of the early universe. This is a picture of the concept that we came up with. There's a deployable aperture diode, a whole bunch of neat hardware there, coolers, star trackers, deployable solar panels. This is what they call a small satellite, similar to what Bristol Aerospace up here are building right now for the RADARSAT Constellation mission, for example. And it's much smaller than Hubble. Here's a cutaway view of the light path. We're looking at developing a 1 meter off-axis telescope. This thing is going to have the biggest camera ever flown. This is an array, a 9x5 array of 4,000 by 4,000 pixel cameras in 3 different colors. This is basically the size of like a 37 centimeter display, all camera. That's pretty cool. It's going to cost about $10 million too, and you don't want to drop it. This is some of the technologies that we've put into it. This telescope here, this is the primary mirror for the European Space Agency's Gaia telescope, which is going to do astrometric mapping of half the Milky Way basically, and measure parallax. It's actually a 3-mirror off-axis telescope built out of silicon carbide, very stiff, lightweight material. This is the detector that we're looking at using. These are the detectors actually that we put in the James Webb Space Telescope right here, which are the kind of the little cousins. There's 4 of these and 1 of these. And this is just a collage of Hubble images to give you an idea. Think of the public outreach potential of something with 200 times the field of Hubble with roughly the same resolution. And we think we can do this for on the order of a couple $100 million. So just to summarize what I've told you, Castor is a concept right now. We're looking to see if we can find international partners to come with us on this for donating the launch, for example, the telescope perhaps, maybe the camera. And we're looking to start early phase studies hopefully next year on this. And so now I have a little video that we produced as part of the study. I can't give you the audio to this because the Space Agency wouldn't let me show it in just English, so I'm going to have to narrate in just English. So dark energy, of course, is the unsolved problem that we're trying to solve with the Castor telescope, mapping the distribution of galaxies in the distant universe. This is a fly-through of the Hubble Deep Field, actually. Someone has produced that. It's free on the web. It's pretty cool. So here it is, the Castor Space Telescope concept with deployable solar panels. It's going to be in a sun-fixed orbit. What that means is the solar panels always face the sun. It's always looking away from the sun. And as the year progresses, it will scan out that plane of the ecliptic, basically, and it'll be able to tilt back and forth. You can see here it is in comparison with the Hubble. It's kind of the small cousin. And you can see how the light will go through this telescope. There will be a fine pointing mirror to give us the sort of resolution that we need. You can see that here's the large field of view. The ultraviolet gives us a lot more information on star-forming regions, energetic areas, and it's complementary to the infrared. It's going to be about 30 times sharper than the state-of-the-art in ultraviolet imaging, the GALAX mission, which is just winding down now. So over the course of its 5-year mission, it's going to map out a huge portion of the sky. And it's basically just going to tile the sky, basically, as it goes around 5 times by imaging in all these 3 different bands. We'll also be able to detect objects in the outer solar system by comparing multiple images of the same region. So, small bodies that you wouldn't otherwise be able to see. Spectroscopic capability will tell us about the composition of nearby stars, red shifts, and we think that this will be a useful tool to help us understand a little bit more about the history of the universe and that 76% of the universe. And by using some of the heritage that Canada has built up on some of these other telescopes, we think we have the capability now to lead this mission. Having just delivered the Fine Guidance Sensor for the James Webb Space Telescope to Goddard, they're integrating that now with the Scientific Instrument Module. And that brings us to the end of the video. If you have any questions, I'd be pleased to take them. Thank you.
Well, Al, would you proceed with partial funding?
Yeah, typically these programs are funded by phase. So we've done a concept study. After this, we do like a phase 0A technology development. We've identified some critical areas of technology that need to be developed a little bit. The filtering, for example, in the ultraviolet is a key technology. We'd have to develop packaging for the camera array to a certain extent. We have to identify who's going to do what portions, work on the requirements of the system. So those early elements can be done, one at a time or as a group in an earlier phase. So yeah, definitely.
Well, this is a good time to do it. The American space thing is down in the dumps, so I think we can take up the slack.
Yeah, and it was well received in Kauai when I presented it to the U.S. So they were the U.S. Ultraviolet community are trying to, they want to get this 10-meter space telescope. So they're thinking big right now, but reality is going to hit them in the face pretty soon. And so the big discussion at this conference was whether they should be asking for a 10-meter telescope or whether they should propose to refurbish one of these 2.4-meter telescopes from the NRO. But really, it's going to cost about the same either way because you're not really saving anything by refurbishing someone else's telescope. And I think the answer is that neither of them are going to happen right away. So this really does come at as an opportune time, and we got a lot of interest from some of the U.S. scientists in collaborating with this.
Great.
Thanks.
Yep. A couple $100 million, that's a bargain, especially when you hear what the governments of Ontario are pissing away lately. Anyway, my political opinion. A couple of quick announcements before we wrap up. Rob Dick, who's not here tonight, is actually hosting his open house at Rideau Ferry tonight and tomorrow. So if you're interested in going down to see what Rob's got there, feel free to pop on by there. You can tomorrow, if you're going to head down there, arrive around 5 if you want to go for dinner, or if you're just interested in checking out the skies there. I'm not sure what we're supposed to get. At 8:30, there's a map there as well, and Rob's phone number is available there, or you can ping him on his website there. Okay. An interesting note. This came up. Barry Matthews is making a 1/10th scale model of the Herschel telescope. So he asked us to put out an announcement, and Rolf, are you still here, Rolf? Where are you, Rolf? Is he? Oh, he's around, eh? Okay. Tell him about this one. Unless he's slumped down in the seat there, I'm not sure. But Barry is actually looking for images of planet Uranus as Herschel might have seen it. He'd like that in conjunction with the model that he's doing. So if anybody's into some heavy-duty planetary imaging, like Rolf there, feel free to submit your images. You can send them our way to Chris or myself. And we'll make sure that Barry gets it. So anything like that of Uranus, that's not a commonly imaged target for planetary observers because it's very small and it's a challenging object to get any kind of detail on. But if anybody's got anything, feel free to forward it. Okay, next one, Chris. And Estelle is here, her pick of the month, The Endless Universe, Beyond the Big Bang. So if you're interested in that, please see Estelle at the end of the meeting. Our usual post-meeting entertainment there is going to be Kelsey's there. Estella is going to have the library open. Al is available, obviously. Coffee and an art are here. You can also see art for RASC membership info and cards. Stephen McIntyre is not with us tonight. Rest of the museum is closed. We had 84 folks tonight. I thank you, everybody, for coming, and congratulations again to our door prize winners. Hope to see that telescope get some good use there. And just a reminder that our next meeting is back to our regular first Friday of the month there, so November the 2nd at 8 p.m. And we hope to see you here. Take care and have a good month, and we'll see you on November the 2nd. Good night, all.